Yeah, hi. In this lecture, in this video, we're going to talk about two sample tests of hypothesis and inferences. And so basically, we are going to cover inferences about two quantitative populations when the samples are large. We'll talk about inferences about two population proportions when we have large samples. And we're going to talk about small sample inferences when the samples are independent. And we'll talk about small sample inferences when the samples are paired, and we could talk about comparing two population variances. So when we compare two population parameters, we use the z-test if we have a large sample, as you remember, and if the samples are small, we only deal with normal populations and use the t-test. So for non-normal, like binomial small populations, we have used different techniques that we cannot cover in this class. So what do we mean by inferences when we have two populations? Basically, we start to think is we have to understand is the parameter of interest. In this case, we are interested in two populations, and the parameter would be the difference between their means. So it's mu1 minus mu2. Okay, so that's the parameter we are interested in. And to make any inferences, whether it's testing hypothesis or confidence intervals, basically that's what we mean by inference, we need to collect data. And so we need to collect data from these two populations that represent with means mu1 and mu2. And the sample we need from the first population, we need the sample size, call it n1. We need the sample mean, we're going to call it x bar 1. And we need the sample standard deviation of the first population, we call it s1. Same thing for the second population, we need this sample size x bar 2 and s2. So how do we estimate this parameter mu1 minus mu2, which is again the difference of two parameters? The point estimator, estimating it with one number, would be simply to look at x bar 1 minus x bar 2. So you take just the difference between the sample means. But the mean of this estimator, mu of x bar 1 minus x bar 2, turns out to be mu1 minus mu2, what this tells me is that my estimator is unbiased, which is a good property for point estimators. Okay? The other thing we want is the standard error, SE, of x bar 1 minus x bar 2, and that turns out to be sigma 1 squared, the population variance of the first population over n1, plus the population variance of the second population over n2. And we take the square root of both of them. Right? And so this is the information we need to do inferences. First, how do we get the confidence interval? So similar to a single population, for two populations, the confidence interval will be the point estimate, which is x bar 1 minus x bar 2, plus or minus the critical value. And since we have large samples, we use z alpha over 2. And now we want the standard error of the point estimator, which is this quantity here that goes there. And so we compute this first by subtracting this quantity and then by adding. So this quantity here, z alpha over 2 times the standard error, is our margin of error. So this is the point estimate plus or minus the margin of error. And so for this formula to be valid, we need our sample sizes to be large. We need n1 and n2 to be both larger than 30. Our samples need to be random, and the samples need to be independent. It means no correlation between the two samples. Okay, and if you remember from previous chapters, sometimes we would like to have our margin of error fixed. So I want, because large margin of error makes your estimation meaningless. Yeah, so I want to limit the margin of error. So what's sample size? And in this case, I would have to have the same sample size for both population. So what sample size do I need so that I can control the margin of error? We call it E. And this is the formula that can give me that sample size. Okay. So N is equal to Z alpha over 2 square sigma. Remember, before we had sigma square over E square. Now we have sigma 1 square plus sigma 2 square over the margin of error square. So that's basically the only difference between what we have here and what we had before for a single population. If I want to test testing hypothesis, again, my parameter is mu1 minus mu2. The data I need: sample size, sample mean, sample standard deviation. For the first sample, from the second sample, I need sample size, sample mean, sample standard deviation. And the way I set up my testing hypothesis is like this. This is my parameter, mu1 minus mu2 equals some value d0. Mostly we want it to be 0, but it can be at something other than 0. And if I have an upper tail test, my alternative would be mu1 minus mu2 greater than d0. So the greater than indicates to me I have an upper tail test, or if the parameter is less than, that indicates to me I have a lower tail or a left tail test, and not equal to, that's the two tail test. So regardless of I'm using an upper tail, a lower tail, or a two tail test, my test statistic will always be the same, which is Z equal the point estimate minus what's on the right hand side over the standard error of the estimate, okay, which is what we had before. And so what's my critical value? So in this case, for the first test, because I have a large sample, my critical value is going to be Z alpha. My critical value in this case is going to be negative Z alpha. And for the two-tail test, my alpha, which is the type 1 error probability, will be split into alpha over 2, and I get Z larger than Z alpha over 2, or Z less than negative Z alpha over 2. So let's graph this and see how it works. And I want to graph this, do it here on this graph. And so let's see. So basically, I want to graph a bell-shaped distribution. And so I'm going to go up. This is my bell shape. And so what determines the type of test I have is the alternative. Say mu1 minus mu2 is greater than some value, so even if it's 0. So this means that my critical value is going to be up there in the upper tail, call it Z alpha. And this point is going to divide this region into two parts. This would be my rejection region. So if my Z, the value I get from the testing hypothesis, is up there, I reject. If it's down here, I do not reject. So we call this non-rejection region. And this is my probability. This is the probability alpha of my type 1 error. Okay, so this is my upper tail test. If it's a lower tail test, if HA is mu1 minus mu2, say less than 0, then I don't know if I can change this color to, no, then my critical value is going to be down here, which is negative Z alpha. and this would be my, in this case, rejection region, and this would be my non-rejection region. And so I would reject if my test statistic value is below. So I have a lower tail test. I would know that if my test statistic value is negative. If it's positive, it would be an upper tail test. And if I have a two-tail test, if I have H0 mu equal, mu1 minus mu2 say equals 0 versus mu1 minus mu2 not equal to 0. This is my alternative. Then my graph is going to look like this. This is not easy to graph with this tablet. So my region here is going to be split into 2 points. In the upper tail I have z alpha over 2, and in the lower tail I have negative z alpha over 2. So this area would be alpha over 2, and this area would be alpha over 2. So my type 1 error splits into both areas. And up here would be my rejection region, which basically this part here and this part here. This is my rejection region, and this is my non-rejection region. So my decision would be if my test statistic value is up here or down here, I reject. If it's in between, I do not reject. Okay, so let's go back to our problem. Where would that be? Okay, I put this back here so this would work. And so that's the graph, the decision, and then we have to state the conclusions. And again, we need large samples. We need our samples to be random, and the samples are independent. So let's do this example here. Suppose we're trying to compare two weight loss programs. This is an example you've seen before. So suppose that we want to test the hypothesis that the two weight loss diet programs are different. So the first program, the old one, we picked a sample of 36. We found that the weight loss in the sample is 21 pounds with a sample variance of 25. So remember, when I use S1 squared, that's a variance. So the sample standard deviation is 5. And my second new program, which I think is probably better or maybe not, the weight loss, I run the program, I collect data, and I have 36 measurements. The weight loss here is less than the first one, so it's 18.5, and the sample variance is 24. D0 is 0 now, and I want alpha to be 5%. Now, can I say that the two programs are different? So if I look here, same sample size, the average loss here is less. But that's based only on a sample of 36 and not on the whole population. So we may or may not be able to say that, because that depends on other factors. It depends on the variances, it depends on alpha. And so putting all this stuff together, we set up our problem, and we have now the null hypothesis. We always put the equal 0 there. So that's mu1, which is the old program, minus the mean of the weight loss of the second program. Remember, these mean weight losses represent the losses for the entire populations. They are unknown, but their estimates these are the estimates of these values, okay, based on a samples of size 36. And we're trying to find out whether the means are equal or they are different. So in this case, we use this test statistic. This is our formula. We substitute x bar 1 is 21, x bar 2 is 18.8, d0 is 0. The sample variance we use is estimate 25, 36, and 1, that's 24, and that's 36. And we Now you need to use your calculator and make sure you got the same number as I got here. Because it's a two-tail test, I know that because this is not equal to, so my critical, and I have large samples, so my critical value is Z alpha over 2, which is 1.96. And so in this case, my rejection region would be, I would reject if this value is larger than 1.96 or less than negative 1.96. So in this case, this value is larger than 1.96, and I can see that if I go up there, so I'm here, and this is my 1.96, and the Z value is up there in the rejection region, and therefore I reject the hypothesis. And so, and then our conclusion, which always we have to say it the same way, at 5%, that's our alpha significance level. It's called also the significance level. There is, if we reject, we say there is sufficient statistical evidence to conclude that the weight loss in the two diet programs are different. So I'm going to leave you with these two exercises to work on. One is to test the hypothesis that the weight loss in the old program is more than, so that's an upper tail test, and to test that the claim that the difference in mean weight loss for the two programs is greater than 1. So you want the D0 to be 1. So in the next video, we'll talk about inferences about two population proportions. And hope this was helpful. Take care.